In this video, we're going to be looking at how Le Chatelier's principle can be applied to chemical equilibrium questions. We're going to focus on this equation of carbon monoxide reacting with 2 moles of hydrogen gas in a reversible reaction to create 1 mole of ethanol and energy. The fact that the energy is on the right-hand side of the equation as a product, it means it's producing energy. It's giving off energy. In chemistry, we call this exothermic. Okay, this will be more important in future class. But for now, it's good to note that energy on the right as a product means exothermic. It's giving it off, okay, exo. So when we start looking at Le Chatelier's principle, we're going to look at how do we stress a system that's at equilibrium, and then how does the system react to our stress? And that's the important piece. So when I look at this one here, the first question says, what happens if the temperature of the system is decreased? So energy and heat are equivalent in these questions. So if I decrease the energy, what happens? Well, let's look at it as a teeter-totter. At equilibrium, the teeter-totter is balanced, okay, with the reactants on the left and the products on the right. But what I've just done is removed energy from the products, making the product side lighter. So the teeter-totter would shift like this. The only way to get that teeter-totter to rebalance is to take mass from the reactants and push it to the other side, to push it forward. That will rebalance the teeter-totter back to level. And in doing so, our reactants are going to go down and our products are going to go up, okay, as we try to maintain or reach that equilibrium again. What that would look like is something like this. Okay, so remember, methanol is blue. So the methanol is stressed, and then all of a sudden its concentration starts going up, and eventually it'll reach equilibrium again. Looking at the hydrogen, okay, remember the hydrogen gas is green. The hydrogen gas is at equilibrium. We've stressed the system. Now we're going to use the hydrogen gas to make more methanol and in turn make more energy. And we're going to do the same thing for the carbon monoxide. We're at equilibrium. We stress the system by removing energy. The carbon monoxide concentration drops, reaches a new equilibrium, and we have a new equilibrium over here represented by these flat lines. Okay. So by looking at the temperature of the system and decreasing it, we shift our reaction to the right, the forward reaction. Okay, so I'll just put a big F there for forward. Let's look at the next one. Okay, so more hydrogen gas is added. What happens? Well, let's look at this very similar to the way we did in the last question. We're going to say more hydrogen gas is added, so that's going to raise the concentration of hydrogen gas. So remember, reactants are on the left, products are on the right. If we look at this as a teeter-totter example, we're making the reactant side heavier. So if we make the reactant side heavier, that side's going to drop. Very similar to the last question, but for a different reason this time. This time we're making the reactant side heavier. The last time we made the product side lighter. But this time reactants are going to get heavier. It's going to drop the teeter-totter. And the only way is to move, or the only way to reach equilibrium again is to move mass from the left-hand side forward to the right. Because remember, these are closed systems. We can't have things escaping. So in doing so, we're going to create more products, more methanol, more energy. And if we're creating more stuff on the product side, the reactant side is going to drop in regards to concentration. So when it comes to the graph, it's going to look very similar to our last question. Equilibrium, we find our stress and we see an increase in methanol and a new equilibrium. And then we see carbon monoxide stressed from equilibrium. It is consumed, reaching a new equilibrium. And then we see our hydrogen gas again at equilibrium, stressed by adding the hydrogen gas. So we have a spike. But then as that spike is consumed, we start to see a drop in concentration again. Okay, and these are not to scale, but just to give you a general idea. So this part right here is the addition. So I'll go plus H2. Okay, so that's where we spike with the hydrogen gas, and then they start leveling off again. So let's keep going. Oh, I should add one more thing up here, sorry. So again, the forward reaction is favored here. Okay, so the forward reaction is favored. Going down to the next one, the pressure of the system is increased. This one doesn't really work as well on the teeter-totter example. So we're going to look at it just from a numerical value. So when we're dealing with pressure, we have to look at the total amount of moles of gas. So if we look at this here, we have 1 mole of carbon monoxide and 2 moles of hydrogen gas. That's a total of 3 moles of gas. Okay, so 3 moles of gas. On the right-hand side of the equation, we have 1 mole of methanol. So 1 mole of methanol. So 1 mole of gas. And the energy doesn't matter in this case when we're dealing with pressure. We're just looking at the moles. The energy will be affected, but it doesn't matter when determining which way the reaction goes. If the pressure of the system is increased, the equation is going to favor the side with the least amount of moles. Okay, so we're going to favor the reactants because it's only 1 mole of gas. Okay, so the chemical compounds have come together into a larger compound, but in doing so, it will result in a lower concentration because it'll have 1 mole of gas over the volume compared to 3 moles of gas over the same volume. So a pressure increase in this case is going to drive the equation forward. What that's going to do is create more methanol, create more energy. It's going to decrease hydrogen and decrease carbon monoxide. And we're going to see the same shifts. We're going to see our methanol go from equilibrium stressed and up. We're going to see our carbon monoxide stressed and start being consumed and going down. And the same thing with hydrogen gas. Equilibrium, we see our stress, we see it going down and then reaching a new equilibrium. This time, however, we haven't stressed the system by removing something, and we haven't stressed the system by adding more into the system. We just increase the pressure by making the space that these gases are floating around in smaller. So that change in pressure could be seen right around here, and we could say that that is just an increase of pressure. Okay, so it's going to favor the side with the least amount of moles. Last but not least, sometimes you'll see things dealing with catalysts with these questions. A good thing to note is that a catalyst doesn't affect equilibrium. Okay, it has no impact. What it does affect, though, is the speed. Okay, so if we were to look at this from a catalyst standpoint with a vessel that had 2 reactants in it and no product, okay, so remember our blue is our methanol, that's no product, it's at 0, we would see something like this. Okay, so with no catalyst, we might see a very slow reaction where it's building up methanol concentration and then reaching an equilibrium. And then we may see something like this where the hydrogen gas is slowly being consumed to a new equilibrium. And then we might see our carbon monoxide also slowly consumed to a new equilibrium. And that's with no catalyst. Okay, so that change of reaction over time, okay, so the delta T, is going to be large. However, if we look at this with a catalyst present, we may see something like this where the methanol is created very quickly before reaching equilibrium, and the hydrogen gas is consumed very quickly, and the carbon monoxide is also consumed very quickly. In this case, we're looking at the delta T, okay, the time for this equilibrium to be reached as being smaller. And that's the effect that catalysts can have on equilibrium. It's just the speed at which they reach equilibrium. Hopefully hopefully this series of questions helps you on your assignment. And if you have any questions for me, please let me know.